Why are sine wave vibrations so common? If we actually construct the mass on a spring system discussed in the previous section and measure its motion accurately, we will find that its xt graph is nearly a perfect sine wave shape, as shown in figure A. We call it sine wave or sinusoidal, even if it is a cosine or a sine or cosine shifted by some arbitrary horizontal amount. It may not be surprising that it is a wiggle of this general sort. But why is it a specific mathematically perfect shape? Why is not a sawtooth shape like, or some other shape like? The mystery deepens as we find that a vast number of apparently unrelated vibrating systems show the same mathematical feature.
Tuning fork, a sapling pulled on one side and released, a car bouncing on its shock absorbers. All these systems will exhibit sine wave motion under one condition. The amplitude of the motion must be small. It is not hard to see intuitively why extremes of amplitude would act differently. For example, a car that is bouncing lightly on its shock absorbers may behave smoothly, but if we try to double the amplitude of the vibrations, the bottom of the car may begin hitting the ground. Although, we are assuming for simplicity that energy is never dissipated. This is clearly not a very realistic assumption in this example.
Each time the car hits the ground, it will convert quite a bit of its potential and kinetic energy into heat and sound. So the vibrations would actually die out quite quickly, rather than repeating for many cycles as shown in the figure. The key to understanding how an object vibrates is to know how the force on the object depends on the object's position. If an object is vibrating to the right and left, then it must have a leftward force on it when it is on the right side and a rightward force when it is on the left side. In one dimension, we can represent the direction of the force using a positive or negative sign, and since the force changes from positive to negative, there must be a point in the middle where the force is zero. This is the equilibrium point where the object would stay at rest if it was released at rest. For convenience of notation throughout this chapter, we will define the origin of our coordinate system so that x equals 0 at equilibrium. The simplest example is the mass on a spring, for which force on the mass is given by Hooke's law, F is equal to negative kx.
We can visualize the behavior of this force using a graph of F versus X, figure E. The graph is a line and the spring constant K is equal to minus its slope. A steeper spring has a large value of K and the steeper slope. Hooke's law is only an approximation, but it works very well for most springs in real life, as long as the spring isn't compressed or stretched so much that it is permanently bent or damaged.
The total force on a vibrating object depends only on the object's position and is related to the object's displacement from equilibrium by an equation of the form F is equal to negative kx. Then the object's motion displays a sinusoidal graph with period t is equal to 2 pi m over k. Even if we do not read the proof, it is not too hard to understand why the equation for the period makes sense. A greater mass causes a greater period, since the force will not be able to whip a massive object back and forth very rapidly.
A larger value of k causes a shorter period because a stronger force can whip the object back and forth more rapidly. This may seem like only an obscure theorem about the mass on a spring system, but figures F and G show it to be far more general than that. Figure F depicts a force curve that is not a straight line. A system with this Fx curve would have large amplitude vibrations that were complex and not sinusoidal. But the same system would exhibit sinusoidal small amplitude vibrations. This is because any curve looks linear from very close up. If we magnify the fx graph as shown in G, it becomes very difficult to tell that the graph is not a straight line. If the vibrations were confined to the region shown in G, they would be very nearly sinusoidal. This is the reason why sinusoidal vibrations are a universal feature of all vibrating systems if we restrict ourselves to small amplitudes. The theorem is therefore of great general significance. It applies throughout the universe to objects ranging from vibrating stars to vibrating nuclei. A sinusoidal vibration is known as simple harmonic motion.